Apologies for the previous two videos, because I forgot to upload them. I recorded them, but I forgot to upload them because I was way too lazy or something like that. And so today we have another, I say a casual integral, but it's actually not very casual because it has an x minus x squared for the base, a pi minus 1 for the exponent, and a natural log term. So quite random sets of numbers and functions inside this integral, and of course this is going to have a closed form in terms of some functions. Now, I was debating about whether or not I should do this one or another one that I planned for later, but I chose this one. But the reason I was debating was because if you're gonna do some work with this, you might end up with the beta function. And I had literally just made a beta function video a couple videos back. So I was wondering if I should do this one or the other one, and I decided, you know what, I'm just gonna do this one because it has a pi over here. Now, enough of my ranting, let's get started. So the first thing you might want to do is factor out this x from the base. And so you would get from 0 to 1, x times 1 minus x, pi minus 1, natural log, 1 minus x, dx. And then you're going to put this into that and that. So I shouldn't actually say put this. I don't know how to explain this. I never learned the names of these tactics. I only know the tactics. And so now we have this. Now, if you just look at this, or if you take my clue from before, you might know that we want to make use of the beta function. And if you find x to some power, 1 minus x to some power, it should remind you of it. Now, the official form for the beta function is the beta of xy, which again we'll define as gamma x gamma y over gamma x plus y is equal to the integral from 0 to 1, x to the, not x because it's already used, t to the x minus 1, 1 minus t to the y minus 1 dt. Now, this might seem actually kind of similar because we have a pi minus 1 and pi minus 1 over here, but we also have a natural logarithm. And this is where things start to get interesting, because now we're going to talk about differentiating the beta function in terms of some variable. So now, since we have 1 minus t as the base over here, and we have 1 minus x as the input of the natural logarithm, we're going to differentiate the exponent of this, which is going to be y. Well, y minus 1, but that doesn't really count. So, for this one, we're going to be taking the we're going to partial differentiate the beta function with respect to y. So, beta xy. Now this is a symbol that we'll probably be using for a while. I'm going to make it a little bit simpler by replacing this delta, this differential part, with a prime and a y. So basically, if you're going to see beta prime with a y at the end, y at the bottom, it means the partial differential of beta with respect to y, and that's probably going to be a lot simpler to understand and write. So this is going to be equal to an integral from 0 to 1 of t to the x minus 1, 1 minus t to the y minus 1. Now, and then you're going to have to take the derivative of this. Now, if you're going to take the derivative of this, it's just this times the natural logarithm of the base, which is 1 minus t dt. Very cool. That's called Feynman's integration trick. And it's also called integrating under the integral sign. No, differentiating under the integral sign. And so now we have, this is just the exact same thing, but we just gotta plug in these numbers here. And now I'm going to break another rule of differentiation, which is going to write this original integral I as beta prime in terms of y, pi pi. You're not really supposed to do this, right? Because if you're going to take the partial derivative of beta pi pi, this is just a constant, and that shouldn't work. But what I'm actually saying here is beta prime in terms of y is a function in and of itself. and then you're plugging in these two numbers. So this is not the same as that, right? This can also be written, I should probably write it as beta prime y of xy evaluated at pi. So this is more weird notation, but I use this while solving, so it's become a sort of habit now when I'm writing this. Anyway, now what we're going to do is we're going to find this out. And what we're going to do, we're going to use this definition right here. So first we need to figure out this beta y prime here. So beta prime with respect to y of xy is just differentiating this, right? So for this one, we're going to use the quotient rule. And we're going to write this as over, this thing is going to be squared in the denominator, x plus y. And then it's going to be, I think if I can remember correctly, it's going to be the derivative of this times this minus the derivative of this times this, I think. So the derivative of, well, I've already lost track. That's going to be, the derivative of this is going to be negative. So yeah. Times the derivative with respect to y of gamma x gamma y. Now, if you're going to differentiate with respect to y, x is a constant, so we can direct that out. And then gamma of x, gamma prime y. We're going to make use of that digamma function in just a second. And then it's going to be minus the derivative of this, which is going to be gamma prime of x plus y. And then times this, so gamma x, gamma y. Oh, cool. Now, and then so now we can do some stuff actually. So we can realize, you can't really realize anything, can you? But you can cancel out these two with the square here. So we just get gamma x, gamma prime y over gamma x plus y. Once again, right, because this thing cancels with that square. And then for the second term, we have a gamma x gamma y over gamma squared of x plus y. So we have, you might want to write it as this, gamma x gamma y over gamma of x plus y. Right, so that takes care of these terms and one of these. And then you're going to go gamma prime over gamma. Gamma prime of x plus y over the regular gamma of x plus y. So if you're going to multiply this out, these two are going to combine to be the square. These two is just going to create that, so this is still red. And now we're going to notice that this is our beta function right here. So we can now replace that. And now another thing to realize, if you were to look at the digamma function, digamma, was it 1 or was it 0? I think it's 0. 0 of x, for example, is defined as the derivative of the natural log gamma. Okay, so this is the definition of the digamma function. Now, if you were to solve this derivative, it would look like gamma prime x over gamma x. And so that's what it is. And so now, if we're going to look at this part over here, that's just this. But you plug in x plus y. So we can now do that. Gamma, or digamma, 0, x plus y. And then now what you're going to do, we're going to look back at this first term. Now, if we're going to look at this and this only, you're going to find that gamma prime of some variable x is going to be equal to gamma times this. So gamma x dot gamma x. Very cool. So now we can plug y into this one. And so now we can get gamma x, and then this one would be gamma y, Digamma y. Okay, very cool. And then over just that, gamma of x plus y. And so now, oh right, and then minus beta xy, digamma x plus y over there. Okay, so now we can look at these two terms. We can ignore that. We notice that this is just the beta times the digamma of y. And so now we can now factor out a beta here. So we have beta of x comma y here times gamma y minus gamma x plus y. Gamma naught y minus gamma naught x plus y. Very cool. That extra parenthesis. Very cool. So now we have found our gamma thing here. And all we gotta do now is just plug in pi and pi for that. Let me actually see. Did I make any mistakes? I probably didn't. So beta prime the y pi pi. Once again, this is just going to be equal to the beta function of pi pi times the digamma function of pi minus the digamma function of 2 pi. Now, I'm sure there are many logarithm properties and stuff that you could use to simplify this one. However, I didn't go really into it because this was just a random piece in my notebook, so I didn't really go all in on the simplification for this one. All I'm going to do now is I'm going to use this definition to simplify this one. And so, we get, as our final answer to our crazily looking integral, this is going to be gamma pi is just gamma squared pi over gamma of 2 pi times the digamma of pi minus digamma 2 pi. I definitely feel like there's a simplification to be made here. I just don't really know where to start because I haven't learned a lot on diagram tricks or anything. So if I do choose to make a better version of this, I'll probably make a second video about it, maybe this week or maybe next week or maybe within a year from now. I will make a video on this one and simplifying it if I could. If I don't, that means I couldn't. Anyway, that is our integral, and I will say goodbye and sorry for this one. And by the way, this one is the rather slightly more casual integral, and I'm probably not going to be releasing a usual integral for today. But yeah, that's it. See you all later, and I hope you enjoy your next 2, 3, 4, I don't know how many weeks that I'm not going to be uploading. See you soon.